So in the previous model, we talked about general spatial modeling, how we might combine multiple layers together to give us a model of some aspect of the real world that we might be interested in investigating. And in this module, we're going to focus on a particular type of spatial modeling, and that's hydrological modeling. In contrast to general spatial modeling, there's a lot of pre-built tools that we're going to be using to sort of create an idea of how water is likely to flow across a given landscape. So what is hydrology? Hydrology is essentially the study of the movement, distribution, quality of water on Earth, including the hydrologic cycle, any water resources, and environmental watershed sustainability. So it's divided into surface and marine hydrology. There's lots of different things that fall into the field of hydrology. What we're really interested here today is looking at surface hydrology, and how things are likely to flow across the surface. What I have up here is the US GIS water cycle, and a sort of infographic of this. And we're not going to be really focusing on a lot of these things. We're not going to focus much on evaporation. We're not going to focus much on anything underground or underwater. What we're really interested in is how things flow across the surface of the Earth. So just one thing that I want to define before we get into it, and that's the idea of a watershed. When we're dealing with a watershed, this is essentially the area that contributes water to a particular feature on a landscape. This will become important a little bit later on when we're talking about the final stages of creating a hydrological model. But this is essentially the physical area contributing to a particular spot, to the water that flows through a particular spot. Sometimes you hear these called basins, catchments, or contributing areas. So what do we do with hydrological modeling in GIS? This really lets us answer a few key questions. How much water might flow across a particular point on the landscape? How is rainwater likely to flow? Where is it likely to collect? Where is it likely to perhaps begin increasing erosion? What areas are likely to have higher water-based erosion? Or what bodies of water might be impacted by a spill at a particular place? So we do this largely through the hydrology toolset in ArcGIS. And like I said, these are already sort of pre-built tools. So we're just going to walk through the process of how to do these, and then in the demonstration we're going to show the physical what you might click to get to each one of these particular tools. So these are tools for modeling how water flows across the landscape. And usually our base layer is elevation. And it's almost always in the form of a DEM rather than a TIN. So if you remember from the earlier module where we talked about topography, a DEM is a raster-based form. And this lets us do some sort of interesting things where we can measure, say, the slope, where we could measure the aspect, all of these things based on the value for one pixel and then all of the ones around it. The hydrology tools work in a very, very similar way. So the DEM is our base data. And the hydrology tools can be very important, again, for understanding rainfall, erosion, spread of pollutants, all of these different things. So what we see here is a flowchart for what we do in a basic hydrological analysis in ArcGIS, where we start off with our DEM, where we might do some different processes to it, getting ourselves to a processed DEM, and then we begin to move into the second stage where we're really creating a lot of this sort of result layers that show us something about hydrology. So our DEM is our base layer. Here we have an example of one with one of our standard color ramps. This is an untreated aster DEM where you can see sort of low elevations in blue. This is actually the edge of a river here, and then high elevations in white. So the first thing we might want to understand is what direction is water likely to flow at any given point. And we do this by creating a flow direction raster. And this is a raster image where the only pixel value is the direction water is likely to flow. So it's based on the slope again. This is very similar to the calculation of slope, just instead of recording either what direction that pixel is facing, aspect, or the angle that it's slope, we're looking at what direction water is likely to flow off of it. So we use the surrounding cells to calculate this. As you can see from these examples here, if we have a high elevation point and then we have lower elevation points around it, it's going to flow towards the lowest elevation. It's pretty simple analysis here. Now the way that it's coded is a little bit interesting in ArcGIS. You can see that they're coded with a value of 1 is east, 2 is southeast, 4 is south, 8 is southwest, 16 is west, 32 is northwest, 64 is north, and 128 is northeast. Now, I went through all of that because I hope that some of you immediately looked at that and said, those are powers of 2. So that's 2 to the 0, 2 to the 1, all the way around to up to 128. So this is essentially the first 7 powers of 2, which is great if we're dealing with an 8-bit image, where we have our maximum value is 2 to the 8th. Now, why do we have them coded this particular way? Well, it lets us do something really, really interesting. If you look at this, if you can't tell which one is likely to have water flowing to it, if it's ambiguous, if it's a flat area, if the 2 pixels to the south and to the southeast are exactly the same, that's going to give us, we can add those together to give ourselves the value. So that could be 7 if it's south and southeast. There's no other combination of pixels, of directions, that would give us a 7. So we can actually understand a little bit about ambiguity in here as well. If we're not able to determine which one's likely to have water, which direction water is likely to flow, we can record that in that pixel value. So this is what one of these might look like if there is a lot of this ambiguity. We have essentially an 8-bit image. 0 to 255, 1 to 256 are our values. So each cell contains the direction that water is likely to flow from it. Now, the next thing that we want to understand is, where are these areas of ambiguity? And usually these areas of ambiguity are because of things we call sinks. So essentially, DEM creation sometimes results in kind of artificial sinks, where we might have where one pixel value just happens to be lower than all the ones around it, where water might be just mathematically likely to collect. However, realistically, we can't collect very much water there, and it's almost always going to flow someplace or absorb into the ground. So a sink is a set of 1 or more cells in which there's no place for it to outflow, where it's lower than everything else around it. So unless these are filled in some way or processed in some way, it's going to isolate portions of the watershed and make it so you can't really analyze how water is likely to flow across the entirety of it. So usually filling sinks is an early stage in processing a DEM for use in hydrology. So if we think about this, we also could have peaks. We could have areas where there's simply, it's higher than all the values around it. These are much less of a problem. It's really filling in these sinks that we end up wanting to do before we get any further. And you can imagine this because if you just have one cell that's lower than everything around it, all of the water from the entire image, that might be thousands and thousands of square kilometers, mathematically flows into that one spot. Realistically, that's not going to happen. It's going to fill up and things are going to keep going downstream. So we want to make sure we process these so we don't end up with these artificial locations of water collection. So if we run the sink tool in ArcGIS, we end up with a series of locations where water isn't likely to flow back out. And we can see those here. They look like black spots. When we do them in the demonstration, they might be on a color ramp. They're just coded by number. Some of these are actual locations where water would collect. Other ones are just part of the process of creating the DEM. So we want to fill these in before we go any further. If there are any sinks, we want to fill them in. And basically what this is going to do is it's just going to raise them up to the minimum value. So it's not going to change how water would flow through that area. It's just going to make it so it doesn't collect anymore in that particular spot. So this is the raw DEM. And this is what it looks like when we fill in each one of the sinks. So if I go back and forth a little bit between these, you can see that there's some areas that were much lower than everything around them that have been filled in. In this particular section of the Earth, these are spots where water would collect if it rained, but again, eventually it's going to fill in and keep flowing back downstream. So we want to model the entire process of water flowing across the surface. So now we're left with the sort of middle stage of processing our DEM, of doing a hydrological analysis, where we have the base data, the DEM with the sinks filled in, what we call a depressionless DEM, and that's what we're going to use to understand everything else afterwards. So when we create our flow direction now, when there are no more sinks in the image, now we don't have any of those sections of ambiguity anymore. Every pixel is going to flow someplace into another pixel. So now we just have 1, 2, 4, 16, 32, 64, 128. We have our directional coding, sort of like we would have for an aspect. So when we've created our new flow direction, ready to go, now we can begin to look at something called flow accumulation. So this is a raster image where the only pixel value is the number of cells flowing into it. So it gives a measure of how much water would flow into a given cell based on what is upstream of it. So if you look at the examples up here, if we're looking across when we start creating our flow direction, it's essentially a count of how many arrows point into that particular spot, cumulatively. So if 5 pixels flow into one pixel and then that one pixel flows into another one, that'd be a 6. So it gets 5 from the one before and then one more for the one that was previously coded as a 5. So we can build up pretty quickly into high numbers here. And this again gives us a measure of how much water is likely to flow through that particular spot. So when we build our flow accumulations, they're built off of the flow direction usually with a little bit of the DEM data in there as well. And this is what they end up looking like. They very quickly begin to look like something that you might consider hydrological, where we have these kind of layers, these lines that represent where water is likely to collect, because these are the spots where lots and lots and lots of pixels are flowing into. In this case, they're scaled from a 0 value is black, so no pixels flow into it, is completely black, up to about 10,000 pixels flowing into the very edges. And those are sort of shown as white with higher ones in there. So it looks very much like a black and white image, but in fact it's kind of grayscaled in there. There's just not a lot of values that are in between very low and very high. Usually it builds very quickly to be high levels or high numbers of pixels flowing into those particular spots. So at this point, we have a lot of stuff going on. We have an entire raster image. We have values for every single cell. Nothing in there is no data. A lot of them are 0, 5 pixels, 10 pixels flowing into them. That's not really very useful information. What we're actually interested in hydrological sense is usually the areas where lots of water is flowing. So we might want to do something called a threshold, apply a threshold to this, where we're just going to throw out all those flow accumulation values that are less than, say, 50 or 100 or something like that. This is not necessary. You can do hydrological analysis without doing this, but it makes the resulting images much cleaner. It makes the resulting hydrological model much easier to process, because you're tossing out a lot of the very low values in there. So what we see in this image is I've rescaled, I've just colored the flow accumulation so that anything that has a value of more than 50 pixels flowing into it is red, everything else is black. So what I can do is just remove those values. Anything less than 50, I just delete it. Anything that's greater than 50, I code it as 1. So once I've done this, I have basically what I would call a stream raster, where I have the streams that water is likely to flow and how they're likely to collect. Now I can begin to order these things. So previously I had some measure of order with my flow accumulation. Areas with higher values were higher, areas with lower values were lower. But what's really kind of important when you're creating a hydrological network is not so much the individual values, but how many other little channels flow into that particular one. So this is where I begin to do stream ordering. There are different methods. There's the Strahler method and the Shreve method. The specifics of them are a little different in how they code, but it's not really very important in this context. If you're more interested in it, I encourage you to look up in a hydrological textbook what the differences between these are. We're going to stick with the default when we're doing this in the demonstration. But basically, no matter which one you're using, each stream feature is ranked by how many other streams contribute to it. So if I have my stream raster, I can do this order, and now they're coded based on how many others feed into it. Now, if you think about it, when you look at this, this is something that would be well represented by vector data. Right now it's a raster, but it would be very easy to create a vector data model out of this because there's lots and lots of sections of no data. The things that we have are linear. So this is where we get to the stream to feature tool that we'll work with. And we basically go through and create a feature layer, a polyline vector layer out of this stream raster, this ranked stream raster that we've created. Now the method that it uses is a little bit different than just simply converting. So if you're doing this for hydrologic data, you want to use this stream to feature tool, not a general convert raster to polyline tool. So then once we've done this, we can code them, we can scale the width of the features based on based on the order, the ranking of the streams. And you see you get something very quickly that looks like a hydrological model. And to be true, if we overlay it on the raster, the DEM, you can see that it follows the topography very, very well. Now we can also do a few other things. We can do what's called a stream link. And this will essentially assign unique values to each stream segment. From this, we can create a more full watershed analysis of the entire region. So it's simply gone through, and each individual segment has its own unique identifier. This again works with the stream raster. We can also do things like what we call flow length. And what the flow length is going to give us is it's going to create a new new raster layer where each cell has a value that is how far water there would travel before leaving the edges of the DEM. So in a lot of these hydrological things, the edges of our DEM are going to be important because that's the furthest out spot we can model. So it can either be upstream or downstream, but if we were to drop a drop of water onto each individual spot in here, it's just giving us a measure of how far it's going to flow. Now this could be useful if we wanted to understand how big of an impact a spill at a particular place is going to be. So essentially it gives us a measure of how long water is going to remain in the DEM we have. We can also do what we call a watershed analysis. And we do this by going through and either measuring how many areas there are going to be to the edge, how many different sections are going to flow out, how many places along the edge of the DEM water is going to flow, or we can do this for particular locations. And these particular locations are called pour points. So one tool that we need to do before we do this is something called snapping our pour points. And our pour points are going to be a particular location. It could be a location of an archaeological site, it could be the location of something that's going to pollute a lot, or if we were going to build a building and we didn't want to have it be in a big erosional channel. However, the location of that point is a vector point, so it's going to be very, very precise. And it may be that we're just a hair over the edge of 1 pixel, or we're just sort of slightly within a higher one than we want to be. So usually what we want to do is move these things slightly so that they match up with wherever the highest flow accumulation within a radius is. This will give us a better measure of what's going to happen at that particular spot. And what this does is it kind of prevents accidental creation of very, very small watersheds kind of on the side of a channel or something like that. So if we create, it's basically going to move our point features. So if we have a series of point features across the area here, if we were to run this watershed tool and see what the catchment for each one of those points is, if we do it for those particular points without snapping them, some of them will hit it pretty well, some of them we won't, some of them will be very, very small, some of them will be normal sized. But if we run the snap pour points tool and then afterwards rerun that watershed analysis, you'll see that we get much, much bigger areas. And these are more representative of how much area actually does flow through that particular spot. So that's an overview of a particular type of spatial modeling, hydrological modeling, where we're understanding something about how water is going to flow across the surface. I've also given you an overview of the tools that we're going to use during the demonstration, so the way that we walk through the process of creating a hydrological model in ArcGIS. Now in the final demonstration, we're going to conclude with a little bit of understanding of how to create three-dimensional data. Some of this could be hydrological, it could be coming from almost anything else that we've dealt with, but it's usually going to be topographic in nature.